Hello, ladies and gentlemen. This is Key Codes Live. It's the first Saturday in the month, so this means I will go live and we talk about different stuff. In this particular live stream, we will talk about the genetic algorithm I wrote for one of my videos, which was the genetic algorithm to create music. And I got a lot of comments under this video in particular that I was lacking line-by-line code review, code comments. So a lot of people had questions how this actually works. And so I thought this is a good opportunity for a live stream. So we will do this today. Very well. So I'm not as well prepared as I would like to be, but I think that's okay because I haven't looked at the code for a couple of months now. So I will go in there with you and go through the code and rediscover what I wrote almost 6 months ago. And we will see and we will understand the code together, I guess. Jeremy, hi. Thanks for the genetic algorithms video. I'm studying engineering and it helped me a lot with some of my projects. You're more than welcome. I'm glad it helped you. Good. Let me just get my screen on here. Put this there. So before we move on, there's one thing I have to say, or I want to say. All right, so this stream is again sponsored by Kite. Kite is a little tool that you can install on your computer that will help you with your code completions in a couple of different programming languages. I use it mostly for Python code, but you can use it for Go, C++, whatever, and it integrates with 16 different editors. I personally use a lot of PyCharm and Sublime Text. So, but if you use something else, it will certainly work as well. So, yeah, I highly recommend it. It's fun. It's especially useful if you are diving into a new kind of framework. It has this little co-pilot here that will actually give you some hints on the code that you're currently writing just by monitoring your cursor on the screen, and it will show you some more information on the framework that you're using. So it really helps me to pick up new stuff quickly. So if you want to check them out, there's a link down in the description below. All right, that out of the way, let's see. Let me just get my notifications. No notifications anymore. And let's go head over to GitHub and see key codes. And what we are going to do is we look at this code here. So if you want to follow along, if you want to install it, feel free. I will post the link to the GitHub repository into the chat now, if you haven't already checked it out. Maybe you can do it, and I will go through it. I will try to understand my own code that I wrote actually 6 months ago, and we will try to, I don't know, just get our head around it, what it does, and how we can use a genetic algorithm to generate music. If there are any questions along the way, just feel free to put them in the chat. Every time I look in this direction, I will look at the chat, and I will try to grab your questions out of there and yeah, answer them. Alrighty. So the first thing that I had to do after checking out this repository was to install the requirements. I added a little requirements txt file there, so you can just go like pip install -r requirements.txt, and it will install all the requirements that we need for this project to run. There's one caveat here. If you are already running on Python 3.9, then you will have a problem with the Pio library that I use in this project to generate the sound. I just tried it again, and it's not really working with Python 3.9. So I had to install Python 3.8 again and create a virtual environment and install the requirements there. So keep that in mind. If you get some errors, try to use Python 3.6, 7, or 8, and then you should be fine. This is the requirements txt. It's actually not many requirements that I use. The main requirement that is actually the heart of everything is Pio, the library that is used to generate the sound for the speakers and to get basically from use Python to generate sine waves and different melodies. MIDI-util is for writing MIDI files, which are used to export the generated melodies and to use them in Ableton to build the song that you may have seen at the end of the video that I posted 6 months ago. And click is a little click is actually pretty cool. Let me just show you. Click Python. Click is something I use every time I write a command line script, because it really helps you with parsing command line arguments. It helps you to have a little like of menu structure in your command line applications. And yeah, click stands for Command Line Interface Creation Kit. So we will see that in the code as well. And yeah, I can't recommend it enough. It really saved me a couple of hours for every project where I want to write my own CLI. And Pio, let's look at Pio again. Pio, Python. I think this one. Exactly. So Pio is a dedicated Python module for digital signal processing. And basically what it is it is a server that is written in C. It's like it says it here. And what we are basically doing, the server starts, and then our Python program communicates with this server, and the server is actually communicating with the hardware to generate the sounds in the end. All right. If there aren't any other questions, I would say we just dive into the code and try to see how everything was put together to use a genetic algorithm to generate sound. Let's see. Maybe before we start, I installed everything. Let's try the program first. So if you haven't watched the video, the other video before, let me just show you what the program is about and how we use a genetic algorithm to generate music. So the file structure is pretty simple. We have this mgen_py, and that's basically the program. That's all there is to it. There's also a in algorithms, there is another file that is called genetic.py, and that is basically the genetic algorithm library or the genetic algorithm functions that we wrote in the videos about the genetic algorithm from scratch. So genetic algorithm from scratch in Python is a video where I explain pretty much how I wrote this Python functions. So if you haven't seen it, check it out. I may look at the genetic algorithm library here from time to time, but this is not the main focus of this live stream. Hey, Spatula, how are you doing? Hope you're great. Jeremy asks, could you do a video on KNN at some point, please? Convolutional neural networks, I guess. Yes, it's on my list. There are a lot of videos on my list, to be honest. And as I was explaining in my last little video where I talked a little bit about what I was up to the last couple of weeks, I try to get around to create more videos for you guys, but my freelance work is really taking up some time. But yes, convolutional neural networks will be covered in the future. Next, so let's try this program out. So we have some input parameters that we have to feed into the program in order for it to generate music for us. We have the number of bars. So 1 bar is 1 unit in music. So, and we can define how many bars we want inside generated for us. So I go just a little quick. I just do 2 bars. The default is 8 here. Nodes per bar, let's do 8. Number of steps. This is basically if you want to generate, if it asks you if you want to generate chords or if you just want to generate melodies. So you can basically say how many different notes you want to have on top of each other. Then it asks you if you want to have pauses between notes, or if it just should be just one continuous melody. And I think yes, we go with pauses here as well. Then there's a key for the scale. If you don't know what a scale is basically a group of notes that sound good with one another. And there are different keys that you can have a scale in. One default key is C major, basically. So we have C, and we use C major for the scale in major. So C major is our scale. And then we can say the scale root. So how high should the melody be? We leave it with 4. And here we go. How many different melodies would we want the genetic algorithm to create? The default is 10. I just reduce it to 5 in this case, and we will get 5 different melodies. Oh, sorry. Yes, I can make the text bigger. Sorry. Here we go. I hope that's better. We go with 5 genomes in our population. So each genome is a melody with 2 bars, 8 notes in the scale of C major. Number of mutations. So each generation, how many mutations do you want? So how many nodes are basically shifted around in our case? So each genetic algorithm is a little bit different. In our case, mutation is defined as using one node and replacing it by another randomly chosen node. Okay, 2 mutations. Mutation probability 0.5 means 50%. So we have a coin that we flip. If it's head, we mutate this node in the melody. If it's tails, we don't. So now I hear the generated melody. I don't know if you hear the generated melody actually. Let me just. Did you hear some sound, or did you just hear my voice? Just see. Can I? No sound. Okay, that's not good. We don't hear the melody. Amazing. Or actually, it's not. I was hoping that it also shares the sound of the screen, but I was mistaken. Share stop screen. Let's try it again. Share screen. Like this one. All right, then we do it differently, and I will use the external mic, and I hopefully you hear the melody through the mic. It's just to give you an idea what the program is actually doing. If you want to see the program in full action and generate a whole song, there's this video I was talking about. Unmute. All right. Do you hear my voice again? I think so. Okay, this is the metronome, and it played the melody, and now it asks me to rate it. So I give it a, from 0 to 5, I give it a 1. Two. That was not so bad, actually. Give it a 4. I didn't like that. I did like the last one better than this one, so a 3. That was not so bad. The best one, I guess. 5. So basically, now we have rated all the 5 genomes in our population, and it now plays the best one back to us. And after I hit the enter key, it plays the second best one back to us as well. And then it will use the genetic algorithm to recombine the melodies, do the mutation, and then the whole thing starts from the beginning. So we get 5 new melodies that we can rate again, and hopefully something better comes out of it. So that was the second best. So it still is pretty rare, but let's just play it a little bit for a couple of generations and see how it unfolds. Okay. Continue. Yes. Two. Almost the same. That was pretty nice. 4. Interestingly, you see, it just played 4 melodies, and I don't know why. So there are actually some bugs in the program as well. I will get to this as soon as we look into the program, because yeah, it's basically just an experimental little script I put together for one video, and the video did better than I thought it would be. So that's why we are here now. Next generation. not sure why it is just playing for. I'm an idiot. I'm an idiot. Of course. So the problem here is that we use always two melodies to generate the children. And I think it is only working correctly with even numbers of population size and not odd numbers, because I think I have a little problem with choosing pairs in an odd number of population somehow. So I think this is the problem. Anyway, let's do it one more time, and then we go into the code if you don't mind. That one is pretty cool. 4. Like that. I don't like that one. That's the same. So this is how the program is working, basically. And you can do this with different kinds of parameters. So if I start this program again, but this time I go on and I just say I just want 1 bar, I want 16 nodes per bar with 1 step again. I don't want pauses. I want to have Dorian, and I want to have it a little bit higher. So let's put it 5, and we do a population size of 6 with a mutation times 3 and a little bit higher mutation factor. We get something completely different. So you see, that was just to show you what different kinds of melodies you can get out of this program just by changing the initial parameters that you put in. All right. The code. Put this away. There we go. Did I make the font a little bit bigger? No. So, put this away. Put this away. All right. I hope this is readable. Spatula. How do you get pio-pip install? Doesn't work for me. Okay. So first question is, what operating system are you on? And the second question is, what Python version are you on? So in the beginning of the stream, I just found out that Pio is not able to work with Python 3.9. So if you are on Python 3.9, I highly recommend that you could generate or create yourself a virtual environment with Python 3.8, 7, or 6, and install Pio in there. So this is the program. The whole program is only 221 lines long. So it's not actually not that much. We use some functions from the algorithms.genetic module. So we might look at these as well. But if you have watched my other genetic algorithms videos, you are pretty familiar with the generate genome function, the mutation function, all of this. because that's not the same. Yes, Pio. That's what I meant as well. You have to tell me on what kind of operating system you're on, and I need to know what version of Python you're running. If you are on macOS and you're running 3.9, then you should downgrade to 3.8 and try to reinstall Pio again. I would suggest we start from the bottom and we go top down first, and maybe later we go bottom up again in order to get the full understanding of the program. So we have this main function, and this is what I was talking earlier about. This is this click library I use, and basically what I can do is I can define a number of parameters I want the program to query or to prompt when it starts, or we can use some command line parameters to actually inject the values that we want. So and another way to just start the program is with --num-bars or --num-nodes, and then it wouldn't ask for the number of bars or the number of the nodes per bar. But if you don't define these values, it will basically start with this prompting, and this is how I implemented the basic start sequence of the program, where it asks you for the different kind of information. All right, Windows 10 Python 3.9. So if you are using Python 3.9, I would suggest that you create yourself that you install Python 3.8 as well, and that you create yourself a virtual environment for Python 3.8. And with that, Pio should be working. I haven't tried it on Windows myself, but I know for a fact that Python 3.9 is problematic with Pio. So in all of these options that we ask the user about will be injected inside of this main functions here in the main function here in the different parameters. So numbers equals numbers, num nodes equals num nodes, and so on. So this is why I love Click. It's really simple to get a nice little command line interface for your program without parsing everything. It just does the hard, heavy lifting there. Every time we generate melodies, our program is saving the generated melodies for each generation and each run into a folder, into MIDI files. So I got this question a lot on the video, where the MIDI files are actually stored, and it's here. So we have this, and we have this. And what we see is that we have this 3 generations that we did today. And in there, we have the MIDI files for starting 5 genomes. And in the first generation, 4 genomes. In the second generation, 4 genomes as well. So, can I open this here? I don't think so. Associate file type. Doesn't matter. So here are the MIDI files of the melodies that we rated in our program run, and actually the order, so the order in which they are saved is descending, best rated to lowest rating. So all the ones with the ending on with the 0, all the files that ends with 0 are basically our favorites for this generation. So the first thing that we do in order, when we start the program, we just get the timestamp and we convert it into a string and save this as the folder name, so that we have the timestamp of the start of the program, so the user knows what take basically it is. So when he started the generation of the melodies, and we save this so we can save the melodies later in the folder with the timestamp. So you see, this is this timestamp of today. Then we just start and generate a random set of melodies, or a genome, random set of genomes, which we will translate later into melodies. That's the little bit tricky part. But we start with a set of genomes, sorry for that, and save that as our initial population. After that, we start the server, which is the PIO server. We need this in order to play any melodies. So we start these at the start of the program. We set the current population ID to 0, and we remember that the program is running, and while the program is running, so every time you remember that the program asks me if I want to continue after each generation run. If I say no, running is set to false, and the program ends. Gracefully. The program ends gracefully. But now the program is running. We have while running, and we start. So the first thing we do is we shuffle the population. So we take all our genomes, randomly generated genomes, and we put them in a totally random order. And now we want to evaluate the fitness for each genome. And if you remember how we do this in a genetic algorithm is, we just hand over all our genomes to the fitness function, and the fitness function returns a fitness score for the genome, so we can rate our population and use the higher rated population entries with a higher probability. So that's what we're doing here. We create a list of tuples of genome and fitness for this genome, for each genome and population. So in the end, we have a list of tuples where we have a genome, and next to it, we have the associated fitness. The interesting part here is we just leave it like this, and we don't look at the fitness function just now. We will do this later. For now, we just think of it like a normal fitness function that we have in our genetic algorithm. We then sort the population. So now we are sorting it by E1. E is, so we use sorted for the population fitness, and we use this little lambda function where we get one entry, E for entry, and we use, so this is one tuple, and we use the second entry of this tuple, which is the fitness. So basically we sort this, our population from the best to the best rated to the lowest rated. And then we generate our new population by just using the genome. Because if you remember, our population starts with a list of genomes. Now our population fitness element has genome and fitness, but we just want to have population should be genome. So we take the first element of the entry, the genome, from our sorted population, which is that we have now our population sorted by fitness and only the genomes inside of a list. I hope that makes sense so far. We take the first two elements of this population and put them into the next generation. This is elitism. We basically have elitism implemented with one line of code right here. So just by taking two elements and putting them into the next generation without even looking at them, we have elitism. And now and here most likely is a little bug. We take for half of our population, for the half of the length of our population. So let's do it in our brain. Let's do it in our mind and go through it. We had a population of size 5. So 5 divided by 2 is 2.5. The integer of 2.5 is 2. So we do for j in range 2 minus 1. So we just do it. We do it for 0 and for 1. We create a selection pair. So we select 2 genomes from our population using this function. I will explain this function later. So we take 2 parents and we do the single point crossover, which means we just use a random point inside of the genome, split them, and use one half of the first parent and the second half of the second parent, and vice versa, and generate 2 offsprings, offspring A and offspring B. Then we use our mutation function, and with the mutation probability and the number of mutations, we mutate offspring A and offspring B and put them into our generation. We do this twice. So we get, we do this one time, exactly. Range 1 is 0 just. It's just once. Sorry for that. So basically because we had a length of 5, 2.5, 2 minus 1, we just had 1 new offspring with a generation of generation size of 5. So we add this to our next generation, and we end up with 4 new genomes, 2 from elitism and 2 offsprings from the single point crossover function, and we have 4 elements in our next generation. That's interesting. Timur, I used your vids on genetic algorithms to make my own music AI genetic algo. That's amazing. That's amazing. If you have a link to a GitHub, we can have a look on it if you want. That's amazing. So after that, now we have this function here, genome to events, and populate. We put in 1, the first element of our population, with a little bit of parameters, and we say for E in events, E play start. And this is basically how we translate our genome into events that we send to our Pio server that actually generates the melody that we hear when we are playing the genome. So here's the number 1 hit, and then we do the second for the population entry number 1, so the second entry, and this is the second best. Then we wait 1 second. We're saving this to the MIDI, so we have a function that is save genome to MIDI. We put it in the folder, population ID, scale, key, and the index in the population, so we have it rated by fitness, lots of parameters again, and we are done. And then we get asked if we want to run again. If we don't enter n, it's still running, and we go into the next round of generation, and we start everything from the beginning. So this is basically how the genetic algorithm works. And it works like every other genetic algorithm that we do with a binary genome. The whole magic is how the fitness function works and a little bit how we use the genome to actually store the melodies. So let's go on. We have talked about the basic overview of this main loop here. One thing that I skipped was this fitness lookup function that we have for the selection pair. So the selection pair function, this is the selection pair function, and it basically needs a population and a fitness function. And with the fitness function, it basically uses the fitness function to get the fitness for each entry of the population and use this as a weight for choosing it. So the higher the fitness is, the more weight it has inside of this sample population. So if the weight is higher, it is more likely to be chosen for the next generation. Our fitness function is a little bit unusual in this time, so we did the following. We calculated the population fitness. So we generated this list of tuples with genome and fitness value. And basically we cached the fitness value for each genome. And the fitness lookup is basically going inside of this list, searching for the entry with the genome we're looking for and returning the fitness value. So we can use the selection pair function, which uses this fitness lookup function to generate the weights for the sample that we are using to generate our parents. And we use the fitness lookup to look into the cached fitness values. I hope that makes sense. So basically, this is how we make it a little bit more efficient and in our case actually workable, because we need this fitness values to be generated once. Because, and now we go into the fitness function, our fitness function is basically playing the melody to us and asks for our fitness value. So this is basically what I did. The melody was played to me, and I entered a number between 0 and 5. And I used this rating as the fitness value that is then used to generate the next generation of melodies. So what does the fitness function do? The fitness function gets the genome. It gets a PIO server. It gets lots of different parameters, which are all used to translate the genome into events, which we are using to play it using the PIO server. So we generate the events, we iterate over each event and play the event on the PIO server. And then as soon as we say start, it actually plays the melody that we transferred using the play function. Then it asks us for our rating. And let me just we have the melody. What did I do here? Interesting. The melody, metronome. Okay. So the events basically are for different, if I could remember correctly, that's where the problem is that I wrote this 6 months ago, but we will find it out. I think the events are played for each voice that we have inside of the melody. Because if you think about it, if we want to play chords, we need to have 3 different melodies played on top of each other. So we start them, and in the end, we stop them, and then we wait 1 second, and we ask for the rating of the user, and if we can't parse it, we use 0 if you ever enter some characters or whatever, and then I return the fitness value, which is the rating. Actually, I have to look up what I did here, but we will go into the genome to events function now anyway, and maybe this helps. So, Prasad, hey, make a video on island-based genetic algorithm. Island-based. Actually, I must admit I haven't heard about that. So, yeah, island-based genetic algorithms. Why not? I will keep that in mind. I have to read up on it actually, and maybe I make a little video on it. Sounds quite interesting, to be honest. And Federico Adrian, if I want to add some simple algorithm related to music theory, like melody pattern or chord, it's better to do when creating population or during the crossover. I would say it's important to do it when you are generating the population. Um, but here are some things that you have to keep in mind. So you can of course use the same genome representation as I did. So you can just use a binary representation of the notes that are supposed to be played. And you can use some algorithms to generate the right chords, and you can put them into your population, and you get some nice melodies from the beginning. But due to the single point crossover and due to the mutation, there is a high probability that you will destroy your population, and that it actually will get worse instead of better, because the population, the whole crossover and mutation phase has no idea about what chords and melody patterns are. So if you want to do that, maybe you need a different genome representation, if you know what I mean. So instead of just encoding the different notes as raw as I did here, maybe you would want to generate whole chords or whole melody patterns and just use the parameters that define this melody patterns instead of the notes itself. So basically you go one abstraction layer higher, and therefore the algorithm is not necessarily able to destroy the chords and the melodies. I hope that makes sense, but I think it's really important to think a little bit about what you want to get out of the algorithm. I wanted to try out if the algorithm can actually generate melodies. If you already put melodies in, then this algorithm, I think, will not make better melodies from it. It will just destroy them. But if you want to have a genetic algorithm that makes better melodies from other melody building blocks, then you need a different genome representation. I hope that makes sense. Island-based is evolving different separated populations that you only cross every few generations. Okay, that doesn't sound so hard to accomplish, to be honest. Yeah, sure, of course. That's interesting. That gives it a little bit more, a little bit different kind of taste, I guess. It's just, yeah. I think the system, the whole evolutionary system has more time to settle down for a good solution on its own, on its island, and then you build a bridge between these islands for 1 or 2 generations, and then everything gets mixed up again. Then you remove the bridge again and let them settle again for a good uh, solution. I don't know if that is worth a whole video. Maybe if I find a good project for that. Oh. It reminds me a little bit of speciation, that you have different species and that you keep the species to itself, and then that new species actually evolve by changing the type of genome they have, and then that's something that I read about, or that I used when I was implementing the NEAT algorithm that is actually used for instance, playing Flappy Birds and stuff like that. I have a video planned on that, so that's pretty nice stuff. Yeah, exactly. That's what I thought. To prevent overfitting, interestingly, I'm not sure why it would prevent overfitting. I would think that each island itself would do a lot of overfitting, because if you run the island and you don't you have a small pool, I would think that the island itself they overfit, but maybe the crossing of the island populations then go makes everything go crazy, and therefore you get a less overfitting model. Yeah, interesting. I will have to read about it. I was working on a project, couldn't find any basic version of it. If you have any source, can you please share it? It would be really helpful. Um, I think Jeremy has a lot of input on this one. Maybe you two can help each other out. I will read about it. I'm sure. Um, but first, I will do another neural network video. I have something planned on cryptocurrencies as well, and then there are some more papers for genetic stuff that I want to put into videos as well. So yeah, good stuff will come. I promise you that. Okay. Um, Local minimas, yes, that makes sense. So if you have local minimas, each of them, the island has a local minima. Then you cross the islands and everything is new, and then you find maybe the global minima at some point. Yeah, I can imagine why this would work. So let's look into the how we actually have our genome and how we can translate that to music. Maybe before I do that, I should just talk about how the genome is actually generated, and then we go to the genome to events function. There we go. So we have this genome to events function. Sorry, I just need to scroll a little bit around here. So generate genome. So our generate genome function basically does nothing more than choosing 0 and 1s for a length. So the generate population function is doing nothing more than generating a bunch of genomes for the size of the population. So the one interesting parameter here is the length of the genome. And the length of the genome is in this case, the length of the genome is up here. Number of bars times number of nodes times bits per node. So basically what we do is if we have 2 bars and we have 8 nodes in each bar, we have 16 nodes in one genome. And then we have a number of bits that we want to have per node, which is 4 in our case. So we have, what did I say? 2 times 8 times 4, 64 bits. And this would be our genome. So we have this idea that every 4 bits, they have a node, and every 4 bits times 8, we have a bar, and this 2 times we have the whole melody that we generated. In order to put this into genomes, into events, we basically do it like this. It's one big list comprehension here. And what do we do first? In order to put it into events, we first translate the genome into a melody. And so I would say that we first look at genome to melody and come back to genome to events later, because genome to events basically just uses the melody construct and uses PIO objects to make it readable or understandable for the PIO server. Genome to melody. So we basically use the genome and we translate the genome into nodes. How do we do that? We iterate over each node. So number of bars times number of nodes is the total number of nodes. So we iterate over each node. And then we take the ith section of bits until the ith plus 1 section of bits. So we actually take every 4 bits and put them into a list. I hope that makes sense. So that's some list comprehension here. So we take 4 bits, and this is 4 bits for each ith node, and put them into a list. So we get a list of lists. Our node length is 4 divided by num nodes. Okay, this is a little bit interesting because the default length for one node in PIO is 4 ticks. So this comes from music. So we have this 4 quarter notes is 1 bar. And this is how PIO works. So if we have, for 1 bar, if we have like 4 nodes, we have a node length of 1. If we have just 2 nodes in our bar, we have a node length of 2. If we have 8, we have a node length of 0.5. Then we create a scale object, which is a PIO thing where we have a root key, a scale, and a key, which is the root, It's interesting. Then we have the scale, and we have the first node, which is the root in my universe, but they use different names for it, and maybe I'm just wrong, but I named the root for the height of the scale. I used the key for the key of the scale, and the scale is the scale. Anyway, so then I generate this melody object here. So we have for each melody, we have the notes, we have a velocity per note. So this is how loud is the note. And then we have a beat. This is how long is the note. And for note in notes, we have our list of lists, which is basically the this what we generated here, and then we go through each of this 4-bit quadlets, bit quadlets, and generate an integer from that. So 0, 0, 0, 0 would be 0, 0, 0, 0, 1 would be 1, 0, 0, 1, 1 would be 3, and so on. 0, 1, 0, 0 would be 4, and so we would generate integers from that. And we then, we have this, how was it? We just think about it. There's one node, there's one bit inside of each. So 3 bits are actually used for the pitch of the note, and 1 bit is used for if it's a pause or if it's not a pause. So if it's not a pause, then if we don't want pauses, we remap all our nodes inside of the 3-bit range. So we use this modulo operator, and we do 2 to the power of bits per node minus 1. So everything is like shifted into 3 bits. And therefore, we don't have pauses. Because here next to this is, if our number is higher than 2 to the power of bits per node minus 1. So if it basically has the pause bit, the pause bit is 1, we just write a note with velocity 0 of note length into our melody, and therefore there is no sound, which is a pause. If it's not, we then have this little block here, which is writing the pitch of the note here, the velocity of the note, which is always 127, and the note length in here. So note length is basically 1. Like I said, if we have 4 notes per bar, note length is 1. But what is this here? So what we have here is, if we have already notes, and the last node that we added to our melody is the same as the integer that we want to add now, so basically the same tone, we don't add the tone again, but just increase the length of the last note. So we don't get, if we have 2 times the same pitch, we don't get e, sondern e. I hope that makes sense. All right. So this is basically how we write our genome into our melody structure that we then use to generate the events for Pio. And then we have the same here, which is basically if we have multiple steps. So what we do there is that we add, for chords, we add number of steps on top of the root node to generate the chords. So if we have num steps 3, we add more nodes inside of the melody. We just put steps append, score, length score for node melody nodes. So we go over each of the nodes, of the melody nodes. Just put this, we just see how this, so we put the nodes in, we put the melody nodes in, we go for steps, append, exactly. So for each node, so 0, 1, 0, we take, exactly, we go 0, 1, 2 for our 3 chord, and we add new nodes on top of the other nodes and replace our normal melody. As you can see, yeah, and replace our normal melody. Nothing, as you can see. That's how it works. Steps, append. And this is how we generate chords. I hope that makes sense so far, but this is really deep and this is really specific to Pio. So, but I think now you understand how I encoded the genome and how I generated from there. I generated the music, and this basically, the genome to events function is basically just translating the melody object that I generated into events that are sent to the Pio server. So we basically use the midi node, which is this for melody nodes, step. Exactly. So is the pitch, then we have the velocity, then we have the beat, and then how long is the note, how fast it should decay the sound, how long it should sustain before it just decays, and how long it takes how long it will last after we actually lifted our virtual finger from the keyboard. And this are the events, and the events are used to be played in the fitness function and down here in the summary for each generation. And I think that's almost it. We have the int from bits thingy, which is just calculating the integer value from a list of 0 and 1s. And then we also have this little thing here, the metronome, which is just something I copied from the Pio documentation, which is basically doing this little ticking noise in order to give you a reference for the speed of the melody. So that is quite interesting, just in order to get a feeling for how fast the melody actually is, if you hear the normal ticking of a metronome beside it. All right then, so I guess that is how the music generation works. I think one thing that was asked was, how do we save the melodies to a MIDI file? And this is the save genome to MIDI function. We give it a file name, we give it a genome, we give it a lot of other parameters. We generate our melody. So we get this melody object with the notes, and here and there we get that. And we generate a MIDI file. We give it one track and one channel. We give it a starting time when it starts. And then we add a track. So basically track and time is this one, track time, track, time is 0, and we give it a tempo, a BPM. So this is handed in as well. And we then iterate over all velocities, and if the velocity is bigger than 0, so if it is not a pause, we then add all the notes for one melody step, so basically a chord or whatever we have, and we add the nodes at this time. And as soon as we are done with that node, we increase the time in melody beats. So this is basically going like this. It's going from left to right, from start to finish, and for each time it's basically setting the nodes, and then it is saving everything to, it's creating the folder first, and then it's saving the file. And that's how we generate MIDI from our genome. As easy as that. All right, ladies and gentlemen, that's it for the part that I wanted to talk about. I hope you found it interesting and you learned a little bit about it and how this program actually works. And if so, yeah, let me know if you have any more questions, and I will be happy to answer them. And now I think we can go over to the open part of this live stream. So if there are any more questions whatsoever, I'm happy to answer them, and I will hang around here for the next 15 minutes, half an hour, whatever. Just get this here. So I see that Prasad and Jeremy, they found each other, they exchanged contact details, and I'm glad to hear that. So hopefully Prasad can get some help with his island genetic algorithm. Perfect. So if there are no other questions, which is totally fine, I think I will stop the live stream and go on and work on some other videos for you guys. And yeah, I hope to see you soon. What are you going to add to this project? I don't think that I will add a lot to this project. This is something I just wanted to try out and to to experiment with, for now at least. And it's basically I just built this to see how far I can go with genetic algorithms. And yeah, it's basically just for the YouTube video. So I don't think I will add a lot of code to this project. All right then. Thank you very much for your time. Thank you much that you were part of this. I hope you learned a little bit. Hope it was fun to watch me struggle to read my own code. And yes, take care. Have a great time. And I see you live next month, and hopefully before that in a new video of mine. Until then, have a lot of fun. See you next time, coders. Bye.